All right, welcome back everyone to the last part of this lecture where we'll talk about finding all solutions to a trigonometric equation. So if I don't give you an interval to solve on, then I want you to find all solutions from negative infinity to positive infinity. And it's actually not that bad because we can use the fact that our trig functions are periodic. So if we were solving an equation involving sine or cosine, remember that these functions have a period of 2 pi. So all we need to do is find solutions from 0 to 2 pi, and then all the other solutions will be one full circle away from those, or two full circles, or three full circles. Or in other words, once we find a solution x, then you can express all the other solutions in terms of taking that angle x and adding on 2k pi. 2 pi, of course, that's a full circle. 2k pi would be any multiple of a full circle. So going forward or backwards by one or more circles from the one solution that you've already found. For tangent, it's similar sort of an idea here. Of course, tangent has a period of pi rather than 2 pi, so we don't have to find solutions from 0 to 2 pi, we just have to find all the solutions from 0 to pi, and then do the same thing as before, where if we have one solution, then that solution plus any multiple of pi would also be a solution. All right, let's give it a try. We're looking to solve secant of x is equal to 2. We want to find the general solutions, and then we also want to find 6 specific solutions. Firstly, if I'm looking to solve secant of x is equal to 2, I'm going to rewrite that as looking for cos of x equal to the reciprocal of 2, equal to a half. And that's, of course, because cosine is reciprocal of secant. I also know that I'm looking for something where cosine is positive, so when I go finding my solutions between 0 and 2 pi, I'll be finding solutions that are in quadrant 1 where cosine is positive, and there'll also be a solution in quadrant 4 where cosine is positive. So next thing, I will think about my special triangle. And I know the special triangle at play here would be the 30, 60, 90 triangle. Go. So we have our 30, 60, 90 triangle with side lengths 1, root 3, and 2. And if we're using this special triangle, we can see that cos of pi over 3, that would be adjacent over hypotenuse, that would be a half. Now, we've found cos of pi over 3 is a half, and that would be the angle in quadrant 1 that we were looking for. We still need to find the angle that's in quadrant 4, and for that, since it's going to have the same reference angle of pi over 3, and it's in quadrant 4, well, then we know that the angle must be 5 pi over 3. So that means we know cos of pi over 3 is a half, and cos of 5 pi over 3 is also a half. So there we go. We found our solutions in quadrant 1 and quadrant 4, our two solutions between 0 and 2 pi. And now we're going to use those to find our general solutions. Since x was equal to pi over 3 was a solution, then taking pi over 3 plus any multiple of 2 pi would also be a solution. And the other one was x could have been 5 pi over 3. That was another solution that we found. And then 5 pi over 3 plus or minus any number of full circles, so plus 2k pi, that would also be a solution. So for my general solutions, I say x is pi over 3 plus 2k pi, x is 5 pi over 3 plus 2k pi, where k is an integer. All right, so we've got our general solutions written down. Now, the next part that we wanted to come up with was some particular solutions, 6 specific solutions. And so the thing to notice here with the formula that we've written, every time I choose a value for k, that will give us 2 more solutions. So for example, when k is 0, if you were to choose a value of k being 0, that would be gone and that would be gone, and you would have the 2 solutions, pi over 3 and 5 pi over 3. But of course, if you were to let k be anything else, if you were to let k be 1, then you could calculate and find another solution for both the angle that was pi over 3 plus a full circle and also the angle 5 pi over 3 plus a full circle. So this is how I'll find my 6 specific solutions. I'll just choose 3 different values for k. For every value of k, I get 2 solutions. So let's do some specific solutions. If I were to have k being 0, then that would give me x is pi over 3 plus 0, or pi over 3. And x is 5 pi over 3 plus 0, or 5 pi over 3. If I were to let k be 1, then I'll get different solutions. If k is 1, then x would be pi over 3 plus 2 times 1 times pi, or in other words, plus 2 pi. And that adds up to pi over 3 plus 2 pi, that is 7 pi over 3. And if x were 5 pi over 3 plus 1 full circle, then x would be 11 pi over 3. And same thing to finish it off, I'll choose k as 2. You don't have to choose 0, 1, and 2. Any value for k that's an integer will produce 2 solutions. So I'm choosing 0, 1, and 2 just for convenience. They're easy numbers to work with, but you could have chosen 11, 12, and 73 if you felt like it. But for k being 2, I would have pi over 3 plus 2 times pi, or 4 pi. And that gives me 13 pi over 3. And lastly, if x were 5 pi over 3 and I went forward 2 full circles, or in other words plus 4 pi, that would take me to 17 pi over 3. So we've now found 6 specific solutions from our general solutions: pi over 3, 5 pi over 3, 7 pi over 3, 11 pi over 3, 13 pi over 3, and 17 pi over 3. And of course, we could keep going if we felt like it. All right, let's do another one. We have 2 tangent squared minus 6 equal to 0, and we're doing the same thing as before, finding general solutions, then finding 6 specific solutions. So first thing I'll do, I'm just going to simplify this. I'm going to isolate the tangent. So we have 2 tangent squared x equals to 6. Divide everybody by 2. So tangent squared x equals 3. And then square root, and that's going to give me 2 equations. I'm going to have tangent of x being plus or minus the square root of 3. So either tangent of x is positive root of 3, or tangent of x is negative root of 3. Okay, so far so good. Now we're looking for the general solutions to this equation, and so we'll look for the general solutions to tangent x equals root 3 and tangent x equals negative root 3. The thing, of course, for us to remember is that for tangent, the period is pi, which means we don't need to find solutions in all 4 quadrants. We only need to find solutions in quadrants 1 and 2, solutions between 0 and pi, because we won't be adding on multiples of 2 pi, because that's not the period of tangent. We'll be adding on multiples of pi. So once we find things within that interval from 0 to pi, then we can generate our general solutions just by adding on multiples of pi. Okay, so let's get into it. We're looking for tangent of x equal to root of 3 or negative root of 3. And if we draw our special triangle, we know that root of 3 shows up in our 30, 60, 90 triangle. If you were to look at tangent of pi over 3, that would be opposite over adjacent, root 3 over 1, or root 3. So we know that one of the solutions is pi over 3. That would be the angle that's in quadrant 1. That would be the angle that gives me the tangent of x equal to positive root of 3. We also need a solution where tangent of x is equal to negative root of 3, but we know where that will be. That will be in quadrant 2, because in quadrant 2, that's where tangent is negative. And we already know the reference angle, too. I mean, we know that the reference angle would be pi over 3. Which means the angle in quadrant 2 should be 2 pi over 3. So the other fact that we had one fact, which was that tangent of pi over 3 was root of 3, so pi over 3 was one solution. We also know tangent of 2 pi over 3 is negative root of 3, so that means that since tangent of 2 pi over 3 is negative root of 3, then 2 pi over 3 is another solution. And now we can write out the general solutions. The general solutions are x is equal to pi over 3 plus multiples of pi, and it's pi, not 2 pi, because pi is the period of tangent, or x is equal to 2 pi over 3 plus multiples of pi, again, because the period of tangent is pi. I do still have to say where k is an integer. There we go. Those are our general solutions. And now the only thing left for us to do is to generate 6 specific solutions, and we know what we'll do with that. We just let k be whatever values we choose, and for each value of k, we'll get 2 solutions. So let's choose, for 6 specific solutions, if I were to choose k being 0, that's where we'll get pi over 3 plus 0, which is pi over 3. We'll get 2 pi over 3 plus 0, which is 2 pi over 3. Okay, I'll choose k being 1. And so that would be going forward by pi radians. So that would be x being pi over 3 plus 1 times pi. And that would be 4 pi over 3. The other one would be 2 pi over 3 going forward pi radians, or plus pi. That would be 5 pi over 3. And just for fun, why not? I'll use k being negative 1. We haven't done a negative value. Doesn't matter whether it's positive or negative, of course. As long as k is an integer, we will still come up with a solution. If we're looking at k being negative 1, then it would be pi over 3 plus negative 1 times pi, or in other words, pi over 3 minus pi. And that would be negative 2 pi over 3. And the other one would be x being 2 pi over 3 plus negative 1 times pi, or minus pi. And that would be negative 1 pi over 3. And so we have now come up with all sorts of specific solutions. Pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3, negative 2 pi over 3, and negative pi over 3. All right, wonderful. Now, there's one last kind of equation for us to think about, which is equations that are in quadratic sort of a form. We've seen this now in several sections in this course where we had things that were exponential equations, but they were really quadratic underneath it all, or logarithmic equations that were really quadratic underneath it all. And the approach was always the same. We would always start off with doing a little bit of a substitution to turn it into something that was obviously quadratic, then factor, and then use that to solve. So here, if I'm looking at what I've got, I have 2 times sine squared x plus sine x minus 1. And if I'm thinking about that, this is kind of quadratic in form in the sense that we've got a constant term, then we have a something, that's the sine x term, and then we have that same something being squared, that's the sine squared x term. So my plan here is if I were to replace sine of x with u, then that means if you square sine of x, that would be u squared. So you would have 2u squared plus u minus 1 equals to 0. And then we would just have to factor that the way that we normally would. And I factored this earlier. This factors as 2u minus 1 times u plus 1. So we'll get two solutions. Either u is a half or u is negative 1. Now, of course, we don't want to know what u is. We would like to know what x is, and this is where we remind ourselves that u was sine of x. So that means really what we have is two equations to solve. Sine of x is a half, and sine x is negative 1. So now we just have two little equations to solve, and we'll do that on the next page. So I'll do the first one, the sine of x equals to negative 1. That's the easier one, because if we're remembering our graph of sine, that we reach the value of negative 1 at 3 pi over 2. That's the point on our sine graph that between 0 and 2 pi, the only time we reach a y value of negative 1 is at 3 pi over 2. So we know that sine of 3 pi over 2 is negative 1, and so therefore we know that x must be 3 pi over 2, that one of our solutions then is 3 pi over 2. Now, I forgot to mention this before we started the question. I read it, but I didn't say it out loud, which is we're solving over the interval from 0 to 2 pi. So here we're not finding all solutions, we're just finding solutions within that first one full circle. So that's why here I only have one solution for where sine of x is equal to negative 1, and that's only at 3 pi over 2. That's the only place in that first full circle where the y value is ever negative 1 for the sine function. Now for the other part, we were looking for where is sine of x equal to a half. And for that, remember that we'll need to do two things. Number one, I'll need to think about special triangles, and I know the special triangle coming into play here is the 30, 60, 90 triangle. There we go. So the 30, 60, 90 triangle, and if you're looking for sine of a half, sine to be equal to a half, you're looking at sine of pi over 6. We know sine of pi over 6, that would be opposite over hypotenuse, 1 over 2, that would be a half. And that would give us one solution, x being pi over 6, because here again, we're looking for the solutions that are in the interval from 0 to 2 pi. And so pi over 6 definitely is in that interval, so pi over 6 is one solution. But we then also need to remember that even though one solution is pi over 6, that there will be other solutions, because where sine is positive is not just quadrant 1, sine is also positive in quadrant 2. So there'll be a second solution in quadrant 2. Now, of course, we know that it's going to have the same reference angle as the solution that we found in quadrant 1. We know the reference angle is going to be pi over 6. So that means the angle that we're looking at in quadrant 2 with reference angle pi over 6, well, that should be the angle 5 pi over 6. So we know sine of 5 pi over 6 is also equal to a half, so we can conclude the third value for us is x must be 5 pi over 6. So for my solution set, we had three solutions that we found. We found pi over 6, we found 5 pi over 6. Those were where sine was equal to a half, and then there was 3 pi over 2, and that was where sine was equal to -1. Okay, so with this question, just sort of to recap what we had, we were looking at an equation that was quadratic in form. We had a constant term, something, and the same something squared, the something here being sine of x. I did a little substitution to turn it into a quadratic equation, solved, so found out what u was, and then worked backwards to find out what x was. And it was basically a lot of the same work that we've done for all the other equations that we've solved. Either thinking about the graph of our trig function or thinking about special triangles. That's how we found our angles. Now, there's one last topic here, and that is equations where there's more than one trig function in it. Because up till now, we've seen equations where there was just one trig function, maybe just sine or just secant, or in the last question, there was sine and also sine squared. But what would we do if we had an equation that involved secants and tangents, or involved sine and tangent, or cotangent and secant? So the idea here is that using some sort of an identity, which includes the Pythagorean identities, and remember the Pythagorean identities, those are the ones where sine squared plus cos squared was equal to 1, or tangent squared plus 1 equal to secant squared x, or 1 plus cotangent squared x equals to cosecant squared x. So if we saw an equation, for example, where there was a sine and a cosine, then maybe I would think about using one of these Pythagorean identities, because then I could use that to turn a sine into a cosine, or an expression involving cosine. Same thing with perhaps if I had secants and tangents, or cosecants and cotangents. For reciprocal identities, those are things like the fact that cosine is the reciprocal of secant, or that tangent is the reciprocal of cotangent. And so, for example, if I had an equation that involved both tangents and cotangents, I could use that reciprocal identity to turn cotangents into tangents. Or if I had an equation that involved secants and cosines, I could turn cosines into secants or secants into cosines. So let's solve one problem here, and this one we've got cosine squared x minus sine squared x equals to 0. And so if I'm going back and thinking about the sorts of identities that I have, I'm looking and I'm seeing the very first identity, that Pythagorean identity at the top. That's what looks like I'm going to be using here, because that would make a relationship between sines and cosines, and that's exactly what I have. I have cosine squared minus sine squared equals 0. So I'm just going to jot down my identity. So the identity that I'm using, which was that sine squared x plus cosine squared x is equal to 1, I could rewrite that and say, well, actually sine squared x is equal to 1 minus cosine squared x. And so the plan here is then I'm going to take my original equation and I'm going to replace the sine squared x with 1 minus cosine squared x. So that means that the equation that I'm actually going to be solving will be cosine squared x minus 1 minus cosine squared x equals 0. Or if I were to clean things up a little bit, that would be cos squared minus 1 plus cos squared x equals to 0, or in other words, 2 cosine squared x minus 1 equals to 0. So now I've got a slightly different looking equation to solve. This is one where I now have it strictly in terms of cosine. Before we get too far into it, one thing to notice here is for the interval, we're looking to solve on that interval from 0 to 2 pi. So that's one part for me to think about. And so now let's continue on. We want to solve 2 cosine squared x minus 1 equals 0. And so next thing that I'll do is, as always, I'll isolate my trig function, so that I would have 2 cosine squared x equals to 1 when I bring the minus 1 to the other side. So cosine squared x is 1/2, or cosine x is plus or minus the square root of 1/2. And of course, square root of 1/2 is the same thing as square root of 1, which is 1, over square root of 2, which is 2. And of course, in simplest terms, 1 over root 2 is the same thing as saying root 2 over 2. So there's going to be two equations to solve here. One is the positive root, where cos of x is positive root 2 over 2, and the other one where it is negative root 2 over 2. Now, conveniently enough, we've seen this before time and time and time again. Root 2 over 2 comes from our 45, 45, 90 triangle, where the side lengths are 1, 1, and root of 2. And so easily enough for us to find that cos of pi over 4 is root 2 over 2. Now, we also have quadrants to consider here. We're looking for quadrants where cosine is positive root 2 over 2, so we would have those in quadrants 1 and 4. But we're also looking for where it's negative root 2 over 2, and that would be in quadrants 2 and 3. So it looks like we're going to have 4 solutions in total, 1 in each quadrant, and it's easy enough with a few quick sketches to figure out where they are. If you are in quadrant 2 with a reference angle with a reference angle of pi over 4, then your angle would be 3 pi over 4. If you were in quadrant 3 with a reference angle of pi over 4, then the angle would be 5 pi over 4. And if you were in quadrant 4 with a reference angle of pi over 4, then the angle would be 7 pi over 4. So there are going to be 4 solutions in total to this equation. Pi over 4 and 7 pi over 4, that's in quadrant 1 and quadrant 4. Those would be the solutions where cos of x is positive root 2 over 2. The ones in quadrant 2 and 3, 3 pi over 4 and 5 pi over 4, those would be the solutions we find where cos of x is equal to negative root 2 over 2. So our solution set contains 4 values. We have 4 angles: pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Lovely. Okay, one last to do. So one more example, and then we are finished for this section. So we're solving for cosine x minus secant x. And so here is where I've got a couple of choices to make. And one is the choice of what identity am I going to use to get rid of one of those trig functions. And so looking back, when we had our identities, we had the Pythagorean identities, which allowed us to make relationships between sine and cosine, or tangent and secant, or cotangent and cosecant, and we don't have those pairs showing up in this equation. We do have the other identities, the reciprocal identities, that cosine is the reciprocal of secant, or secant is the reciprocal of cosine, and since my equation has cosines and secants in it, that seems to be the wise choice for my approach. I'm going to, since I feel happier having everything in terms of cosine rather than secants, I'm going to keep the cosine, and I'm going to rewrite secant as being 1 over cosine of x. Okay, so next, what I'm going to do is I'm going to multiply everybody left side and right side by cosine of x. So in the first term, I would have 4 cosine squared of x, cos x times cos x. The second term, 1 over cos x times cos x. The coses would cancel, leaving just 1. And 0 times cos of x, that would just leave me with 0. And so now I'm going to isolate the trig function. And then do the same thing that we did before, which is cosine squared x is equal to a quarter. So cos x is equal to plus or minus the square root of a quarter. And the square root of a quarter is root of 1, which is 1, over root of 4, which is 2. So in other words, we have plus or minus a half. So we'll be looking for where cosine is positive a half or negative a half. The other thing to notice here before we go further and before I change the page is to notice that we're solving this equation and there's no interval given. So that means we don't just want a few solutions, we want all the solutions. We're looking for the general solutions to this equation. So this means that we are going to find all of our solutions in the interval from 0 to 2 pi, and then take those solutions and add on 2k pi, add on multiples of full circles to them to get all the other solutions in all the other circles around that we could be traveling. So let's first find our solutions from 0 to 2 pi. And for that, just a little quick sketch for ourselves, of course. We know that if we're looking for solutions from 0 to 2 pi, that cosine would be equal to positive a half in quadrants 1 and 4, and equal to negative a half in quadrants 2 and 3. The other thing that we'll remember is that a half, we do have that showing up in our 30, 60, 90 triangle. That if you're looking for where do we have a cosine value of a half, that would be for pi over 3. That cosine of pi over 3 is adjacent over hypotenuse 1 over 2, or a half. So one of the angles, the one that's in quadrant 1, is pi over 3, and then all the other ones will all have reference angles of pi over 3. You'll have in quadrant 2 at 2 pi over 3, that's where cosine will be negative a half. In quadrant 3, at 4 pi over 3, that's where cosine will also be negative a half. And in quadrant 4, at 5 pi over 3, that's also where cosine will be equal to positive a half. So I have two quadrants where it's equal to positive a half, or sorry, two angles where it's equal to positive a half, pi over 3 and 5 pi over 3, and two angles where cosine is equal to negative a half, that's 2 pi over 3 and 4 pi over 3. So those are the four angles between 0 and 2 pi. And so for my general solutions, I'll say that my general solutions are pi over 3 plus any multiple of a full circle. We have 2 pi over 3 plus any multiple of a full circle. And we have 4 pi over 3 plus any multiple of a full circle. And 5 pi over 3 plus any multiple of a full circle. So these are all the solutions, or in other words, these are the general solutions to that original equation. I should just write here, of course, and I have to, that where k is an integer, and then there we go. So again, remember that the reason we're adding multiples of 2 pi, the reason why it's 2k pi being added to these angles, is because cosine has a period of 2 pi. So whatever solves the equation, add on or subtract multiples of 2 pi, that will also be a solution to the equation. So since pi over 3 is a solution, then pi over 3 plus any full circle or minus any number of full circles would also be a solution. All right, good work, everyone. So that's the end of 8.3, And so you have to look forward to 8.4, a really interesting section where we're going to be establishing some new trigonometric identities. We've already had some that we've seen before. We've had the Pythagorean identities and the reciprocal identities, but there's lots more different identities that exist out there between our trig functions, and we're going to prove that these identities hold. And that's what we can look forward to in 8.4 when I see you all next.